Okay, thank you for coming. And this is gonna be a kind of a chronicle of my pains through trying to learn AI. To remember in 2021, I decided to resign from being the director of undergraduate program. That was the main reason, because I thought there was no way I was gonna be able to learn this while I'm juggling between administration and academics. So this is just a sample trying to show you how I went in. You don't have to go. There are a lot of mistakes I made. I'll tell you the mistakes I made. I don't want you to make those mistakes. At least make it easy for you. There's no way you're gonna avoid AI anyway, if you are still thinking whether you can wing it. So that's the other reason for doing this. So the outline here is very simple. I will give you my motivation. I've already started on that. And then the some of the challenges and my approach and what we found. The motivation came from my former student, Lorraine Hyman. She's the person in charge of all the tide gauges in the US. That includes Guam and all the territories. And she came to me and said, "Do you remember your lecture on tides?" I said, "Yeah." And she said, "Currents can be crazy, can't they?" I said, "Yeah, I know that." She said, "But not the crazy you think." I said, "How?" She said, "You got to go to Columbia River, then you'll know how currents can be crazy." And she showed me plots she had made. I said, "Wow, that's interesting." So, there are reasons why. I'm gonna explain why Columbia is special. So, but what I did, like everybody does, I decided to go into literature and try and see what do people know about Columbian stuff. And there's this gentleman here, David J. He's a former student of SoMAS, MSRC. He was a Malcolm Bowman student, and kind of a crazy guy. Yeah, but he's got it upstairs. So he's come up with lots and lots of different ways of analyzing the non-stationary tides, which I've not so far explained to you what they are, but I'll tell you in a minute. Right. So first of all, let's go to Columbia and figure it out. This is the Columbia starts there, and it's got a lot of tributaries. And here, so mark where I have all these purple arrows, and at Bonneville or Bonneville, there's a dam. And that controls how much water flows upstream. But you might think, okay, having one dam is a problem, right? Oh, I didn't do that. I should have said that. Columbia has got something like 130 dams. It's just nuts. I've never heard of a river having 100-something dams, and dams are everywhere. So the one of the stations I want to look at is that one. That's what everybody's been scared of. And also compare it to Astoria. Astoria is kind of semi-well behaved. So that's not much of a problem. And what Lorraine was trying to do is all these red triangles, she's trying to install these new ones and put ABCs, trying to figure out so that we can get navigation through the river. That's the whole point. So what are challenges for non-stationary tides? And before I go to that, let's go to tides. Simply put, it's just a gravitational competition between gravitational and centrifugal force, right? And if there is anything predictable in ocean science, which some think are tides, you can predict the tides 100 years from now, and most probably you'll get it right. Only if it's on the coastal water and there are no issues with the bathymetry. That's a big condition. Now, most ports are not just outside with talking straight to the ocean. They are in estuaries, in rivers. Think of New York City, think of Baltimore, whatever, whichever you pick, it will be an estuary or a river. And that's where the problem begins, because now you have competition between the sea level changing and the river discharge, right? So it's the river discharge which tends to kind of mess up things a bit. And for most part though, you can just use harmonic analysis, the least squares. You just set up an equation, and I'll show it later. It's very easy to do this. And usually, strictly speaking, you're supposed to go to about 130 different components, tidal components. There's the lunar semi-diurnal, solar semi-diurnal, and the unisolar, and it goes on and on and on to about 130. What NOAA uses is that between 35 and 37 components, frequencies to fit the tide. And people have developed the tide. Always devote the T-tide, and then Kolga from Yukon, if we move to URI, he developed the U-tide, which is just a simple modification of that. T-tide had strict conditions that the data had to be continuous, but U-tide allows you to do that. So what is challenging about the non-stationary tides, if you take the long-term average, it's not a straight line, not even near a straight line. Because, so the baseline keeps changing because of the river input, right? Does it change even if you are not on a river? Yes, it does. If you have a storm, it will change that, right? And the interesting thing, which I didn't know, I got to know this when I was teaching MAR 350 this spring, is when the sea level rises, like when you have a tsunami, it can do the reverse, it can affect the sea level pressure. And I thought it was always one way, but it's a two-way process. So there are many reasons, and that's what the mechanisms have listed there. But for the non-stationary tides, it's the abruptness in changes. If it was changing slowly, you could catch it. If you do, you can filter it out. But once you have these abrupt changes, they tend to change the amplitude and change the phase, then you are in trouble. Because then you can't track the frequency you going to. So, and how can that happen? If we go, normally we want to expand so we can have bigger boats, bigger ships getting into ports and stuff. If you change the depth or change the width, that will mess up the times. And what else? The other stuff is not sure. So what I'm showing here is the different tidal records on the Columbia River. And I got this from Lorraine. And you can see this, anybody who knows about tides, you see, you look at that, you know, there's no way you're gonna use harmonic analysis to figure out what the frequencies are. Right? Unless you filter, you can filter it. But when you filter, you have abrupt changes like this, like that, that's not gonna work very well. So what is, I've been singing about harmonic analysis. I'll go very quickly for some who are not familiar with that. Or what you do, just say the sea level, the fluctuation which you're seeing is a function of the, let's call it stage, the base height, and then a sum of all these cosine terms with different frequencies. And those are the components I was referring to. There are 137 components. So, and that's okay. But if you introduce the river, this doesn't sit very well because it messes up things a bit. So Jay's group, the one I referred to earlier, they said, okay, we can make that simple. Why don't we put all the terms and then include the river discharge? Makes sense? So as long as you know the river discharge, you can include the impact of the river on your tide. And then you introduce a lot of different fitting terms. This is just a fancy way of getting all the different terms so that you fit it. It's curve fitting, that's what I call it. But the important terms here are the river discharge and the diurnal range, the tide downstream near the coast is also important. So you do some fitting, you get it right. Then that method works well for Astoria. If you did it for New York, it would work. For Bridgeport, it would work. It does not work if you go to Yangtze River. It does not work on Columbia if you go past the Astoria. And tidal currents, which Lorraine is worried about, forget about it. So that's what made me kind of get interested in this. Said, okay, maybe I could try and do this. So I thought. So I'm lazy, so I decided to go look around and see if anybody has done this. And there's a guy, he's a former student, I didn't know, he's in China. So I wrote to him and Haidong said, oh, I've got this S-tide. I looked at the S-tide, but it was a simple modification of the S-tide. What he did was to include what is called the coastal upwelling index, which makes it work better than S-tide, but it does not solve the fundamental problems of S-tide. It's still stuck. So I said, okay, keep looking. And then I got that paper and it was okay. Then I got excited about this paper from Taiwan and wrote to these guys about 3-4 times. You know me, when I keep bugging you, I don't let go. And all my 4 or 5 times didn't work at all, which was good because then I had to sit down and say, okay, now I've got to do it myself. I decided to first read what he had written about, and he was referring to the deep neural networks, and I had already started learning a little bit of deep neural networks. So I'm going to describe this a little bit because it's the main part of what I do, but I have modification on what he did. Because in reading other papers, especially papers from engineering, it showed one of the biggest problems in terms of predicting, especially for the civil engineers, is predicting traffic past the point. It's a pain because it's not nature. You have, once you introduce humans, you are in trouble, right? So everybody who will try that, the maximum they can get is like 0.67 of R squared. So that even with the best of function models we have. So I decided to take their approach and use that and modify Young's method. That's why Young's method is important. So I'm gonna go slowly now. In deep neural networks, you have neurons. I will bore those people who know about machine learning. You have neurons, and with the neurons, what you are trying to do, you are getting data, your input data, you are feeding it to the neurons, to almost every neuron. And all you are trying to do is trying to estimate a weight. In fact, you are guessing. You can guess that when you start, you can guess that all the weights are 0, or you can guess all the weights are 1. And then it will keep changing itself, keep guessing, getting right, there's a loss function. So loss function is kind of a punishment to the system. You get it wrong, you punish it according to how wrong it was until you get it right. So in here for the LSTM is the long short memory model, and it's from the TensorFlow system. But even PyTorch has a similar approach. So you put in the data, and what it has a beautiful forget gate. This is the most important part. It allows some of the data that to keep some of the weights which were wrong. It keeps them. Whereas most systems, if you get it wrong, that is thrown away. You are looking for a new one, you keep updating, and it goes on like that. But not LSTM. So that allows it to have some kind of memory. Like next time you update, it looks at what you had before again in order to make it, to update your weight, which is really clever. And at the end of the day, you get the data. I don't want to belabor you with that. Anybody interested, you can sit down, I'll explain that. Right. So to make Christopher happy, because if I don't do that, he will be upset. When you are trying to update, say, a memory set, you go in there and the activation function here is touch, right? And the touch, because it goes like that, it starts with -1, goes to 1, and saturates again. So that curve allows it to be able to take in nonlinearity very well. It handles nonlinearity very well. But you don't have to use touch. You can use sigmoid, you can use real linear function. It's called RELU, and a lot of others. But I like touch. It tends to be very well behaved. And if you have GPU, you have a GPU, you better stick to touch. Otherwise, you might get in trouble. At least on the list. So these W's are the weights which are gonna keep effectively changing until you get to the output gate. And when you are outputting, again, you need the touch. So as I said earlier, you have the input data goes in to all the layers in between, if you do have them. So with the reason why it's called the deep learning is because most of the machine learning, like if you take simple ones like random forests, you take XGBoost, cat goes, all of them tend to go from here straight to there. They have only one layer. But with deep learning, you can have several more. And the LSTM also uses another clever system. You don't want to overfit your data because you can run your model and get beautiful answers when you test it. But if you overfitted it, it will not work very well once you go to data it's not seen. And to allow that, what LSTM does, it chops off some of the data, randomly picks the neurons to switch off. All you do, you tell it, I want maybe 50% of my neurons to be switched off, or 10% of my neurons to be switched off. And it will switch those off, so it will only allow a few of the connections, and those will be your weights. Next time around, you run it, it will be picking different neurons to fire up. So that's how the LSTM runs. And then to test the model, uses the common model metrics. You can use the root mean square. I normally use the mean square error, and you can use MAPE, or you can use the mean absolute error. Depends on your choice. That doesn't really matter here. I'll choose that, and of course the correlation coefficient. So then I decided to go back. After I knew how to run this, I said, okay, let me go back and see what other people are doing. And there is Zhang, 2020, he was doing almost what I wanted to do. And in fact, when I read this, I was very disappointed. So that's what I was going to use. And I thought, okay, if I do that, he's already done it. Because what he did was to take the NS tide from Jay's group, actually Pascal Matt, his former student, is the one who told you. So he takes the NS tide, he predicts, and then he gets the error the model makes, feeds that into LSTM. And that way, kind of a clever way, so he can predict the error the NS tide is going to make, which means he can always come back and correct it. And he's already done it, right? So, but there is a catch. This is beautiful, it works, but it cannot, it is good for analysis, but it's not good for prediction, the true operational prediction. Do you know why? Because it depends on the river discharge. If today at 12:30, I want to predict what's going to happen next week, NS tide will not work. S tide will not work. Why? Because they need the river discharge. I don't have the river discharge for next week, right? So I thought, okay, so maybe just as well, somebody has already made the mistake I was going to make. So I had to think of another way, and I decided I'm not going to go this way. I'm going to treat it as a multiple variable regression, but there's a time I'm going to switch off, drop off all the other factors and then remain with the time. Then it's as if I'm predicting stocks. It's just any signal you're doing time series analysis without bothering what the factors are. Okay, so I decided to be clever for once. I decided I was not gonna go and attack Columbia River because everybody has been screwing up Columbia River. So I'm gonna go for the easy one. Why don't I pick Bridgeport? Bridgeport has got the longest tide in Long Island Sound. And I assumed, and I pretend to be the expert on tides, I assumed, there shouldn't be any problem here. One, the Connecticut is somewhere here. it will affect, but it won't be big. It's already in the sound. So I should take this. I was wrong. The Connecticut affects this. The Usatonic affects this. Right? And then I said, you know what? Let's go to Essex, which is a little bit more difficult. So it will be a little step above, but it's still very near the coast, so it shouldn't be a problem. Turned out this was the most difficult station I could have picked, but we'll see later. So the other one is, which we've already seen, I decided to pick Vancouver and Astoria for the Columbia River. So once I'm done with the Long Island Sound, I'm sure of what I'm doing, I'm gonna come back to this. So that's Bridgeport data. Let's go through that. If you took data, the tidal data from Bridgeport, you will get the blue, not the green. That's the blue signal. Right off the bat, this is 2018. Right off the bat, you can see there's a huge shift. And maybe that could have been a storm, can't be a storm, right? And it goes on, you get these, and I decided, okay, why don't I filter it? I use, normally in physical oceanography, if we are removing tide, you use a 34 low pass filter. And that's what the green is. So if you do that, then you get this, right? If you filter the data. And for tides, that's clean. I can use harmonic analysis and my answers will be right. There will be no problem. But that was not my interest. My interest was to see how is the green related to the river discharge. And what I was doing in my LSTM, I was taking the whole year and then chopping off the December part, this bit. So I use January to end of November to train and test my model. And after I'm done, so the model never sees the December data. And then after that, I see how well I can predict this. So let's go slowly. Here in November, you can see this bit where it goes up. It should be some kind of a storm. It's a low pressure system coming through, right? Because the water level is going up. So it must be a low pressure system coming through. And that one, same. But then we have other ones going downwards. And those, they are not a low pressure system, but when you look at that, they seem to be aligned with what the river is doing. So it's a combination of the river and the low pressure system. If you go to Vancouver, now let's go to the Columbia River. We know what is happening in Long Island Sound. And that's the little patches are the tide. So here you see the river is changing, but not driven much by tide. Tide is tiny little thing. And as you go throughout the year, if you filter that data, just like we did for Bridgeport, this is what you're gonna get. Now, this is interesting. One, it tells you the amplitude of the tide is not constant, keeps varying from the late winter to late spring, and then things quieten, and then it goes nuts, right? But it's tides, right? So, and here, which is not seen, and I do want to go into that, but the frequency also gets shifted. And that's what That's what has been driving people who work on Columbia crazy. So what I decided to do, I said, okay, I'm going to use sea level pressure, the upstream water height, like I'll go up the river farther than where I want to be, just to check what the river is doing. Because everybody was saying that is important. And river discharge, and then I chose year, month, day, hour. I didn't use, well, I used time. Time didn't work very well. It kept shifting the phase. So I decided to drop year. I kept month, day, and hour, and that worked. So these go in as independent variables. They're independent features. And then sea surface temperature, wind, and the tidal range. So the target is the tidal elevation. What happened when I ran the exploratory kind of work analysis, these ones didn't contribute much. Tidal range was not that important. Wind was not that important. And sea surface temperature was almost important. Oh, because it's seasonal. What it does, the water just expands because of heating during summer, and then it goes down. But it's tiny little bit, doesn't matter. These are the ones which matter. So I kept these, dropped these ones.
So just a question there.
Yes.
So your sea surface pressure, sea level pressure, and river discharge and height, are they, because you want to predict your height, so
Yes.
are they before the prediction only, or?
I'm gonna come back to that, and then let me answer part of it. So this was trying to go along with what everybody else has been doing to see how much power do these contribute. Because if I found that they are extremely important, right, then my story would be dead. I wouldn't go any further, right? But what I did was I found that they were important, and then I would split them. One, I'll do each one separately, and then I kept combining them, trying to see how they were gonna, what contribution they were gonna have. And finally, the whole reason of splitting my time this way, I took these off because otherwise I would run into the problem Zhang et al. Did run into, right? Because I wouldn't have the prediction of, in fact, I tried. I looked at the prediction of the sea level pressure system and the wind and all that kind of stuff. The errors are so big in those predictions, they just throw you off, right? So I decided to drop. So at the end, you see that I take these and throw them away, and just remain with that bound. Okay, so as I said, my approach, I had to go to Madrid and learn how they drive there, and then figure out how I would modify that model to fit my situation. And what my model does, I take a convolution block and I combine it with LSTM. But the LSTM is not exactly what I described. This LSTM is a double LSTM. That's why it's called bidirectional. So it's doing this. And the reason for doing that, I wanted it to look even further than the normal. The LSTM remembers things, but it doesn't remember enough for what I was doing. The type data needs to be typed in terms of phase. I didn't want to allow the phase to keep dancing around. So that's why I decided to use the by LSTM. And it looks further, my look back value can go further back without making the model unstable. And what I used between 24 and 48 hours. And that seemed to be working all right. If you make it too long, then you start getting overfitting issues. What else? And then I tried to see if I could use, there are people who have used 50 hidden layers, which I think is crazy. But and some I used 6. I tried to use 6, 5, and when I compared it to one single layer, they are the same. In fact, single layer sometimes would outperform it. So I did not include hidden layers in this issue. So I've just got these 2 LSTMs looking like that. And the metrics I used, as I said before, is the mean absolute error, mean squares error, correlation coefficient, and maximum error. I just wanted to know how, if I want to use it for operation, you don't want your boat to be stuck in the mud, right? So you can get, this can be small, but if you get this to be large, you're dead, right? So I thought I would explain a little bit about, very quickly this, I should explain what BiLSTM does. The normal one goes this way to the output. So if you have the BiLSTM, you have this path, but then you also include this, which is looking backwards instead of looking forward. And they all go in the feed, so they will eventually be affecting the weight you're going to be calculating there. These are the 3 machines I used, depending on what my student Reza was allowing me to use. You get to be pushed around if you're a professor. I didn't know that, but so I decided to spread my models across all the machines. If I'm pushed from one, I'll just use another one. So the setup I had is the look back of 48 hours. I used 500 neurons to start with, but later on I figured even with 150 neurons, I was getting very reasonable answers. There's no reason for that. The batch size is 15. Batch size is how much data do you take at any particular time. And the epochs is how many times you're gonna repeat this. You keep shuffling and run it over and over and over and over. So depending on the power you have, you can run it as long as you want. So, the code snippet which I wanted to tell you about was, this is the CNN, and then the pooling here, and the by LSTM is here. Dropout, once I started using, beginning I wasn't using GPU, but after I started using a GPU, there was a lot of advice that you should drop that, and I dropped that. I didn't see any issues with that. And this is how you punish the model in case it makes anything wrong. So these are the guts of the deep neural network. Everything else before is just how you input, how you condition the data, and how you output your data.
Just tell me, how do you know how much data you have to?
You have to have.
Yeah.
Good question. You should ask that question. You should ask Henry, not me. But let me try and answer. One, if you are me, you do the try and error. you put it in and you see, does it work or not? Because if there is if it's not enough, it will not do the right prediction. And however much you pump it, you can increase the neurons, you can increase the hidden layers, you can do all those things. If the data is not enough, it's not enough. I think that pretty much it comes. But Henry later on maybe might make a comment on that. Yeah, you shouldn't be asking me first, just ask Henry. That's the normal. So, so these are I took 2 years, 2018 and 2021, and the reason why 2018 was kind of average kind of year, and 2021 was just great for some reason. So I decided, let me take a different year and this is the month of December, as I told you. I'm just looking at the month, how well can I predict December? And see here, pretty well, but it starts to die off by the time you get to like 200 hours. These are hours from the beginning. And so, and with 2021, there was already trouble even in the beginning and in the first few days. And that was Bridgeport, the well-behaved. And here you have a summary. Remember, I said that I took the combination of those different variables which I thought were affecting the tide, and the sea level pressure, that height upstream and time gave the best combination. But if you drop the sea level pressure, still about the same. If you drop them all and just use time, the difference is very little. If you look at R squared, that's 0.95, this is 0.94, there's not much difference there. So why do I need to carry this? Then I'm home free. I can just use time and I'll be able to make a good prediction. And the same thing, in fact, for 2021, for some reason, the time one had the best system instead of all these other ones, right? And all the time I'm trying to compare with the T-tide, and especially for Bridgeport, that is important because we know T-tide is what is being used now with NOAA. So for FX, you can see things are not very good for SX. The best we could come up with our model is 0.77, and the T-tide, the standard, you can see is 0.68. So the T-tide struggles badly with the SX data compared to LSTM. And that's the prediction. Some things don't go right, but overall it wasn't very shabby. For a crazy signal, I don't think you can call that shabby. Let's go to Columbia River. So Columbia River, those are the prediction. And again, if you look at Astoria just before 200, we're making some few mistakes, about 25 centimeters, but 25 centimeters is about that much. I don't think I'm gonna mess up a boat with that, especially if I'm in a tidal range of about almost 4 meters, right? So that's a very small mistake, and that's the maximum mistake. For 2021, for Astoria, still we're looking at, it jumps a little bit. Now we are getting almost 0.5 meter. It's on the borderline. Confidence is running low there. But the summary for Astoria is that, and you see the best prediction is coming from time alone. I'm forgetting about all these other variables. Even for Columbia, that was impressive. And 2021, still for Astoria, the time one is the one which holds better than the other one. This big, but there's very little difference between this and that. Now we go to Vancouver. Now we are playing, right? One, looking at this is crazy. If you see that observation and say, oh, can you analyze this? That's like a joke. You say, no, I can't. But what impressed me though, it is wrong, but what impressed me was how LSTM, how it manages to remember and know how to go up and follow it. Yeah, the errors are huge. It's almost like a meter, right? But the fact that it even got that trend before it fell off, by the time it gets here, it's just lost it, right? And you can see the prediction is going its own way and the observations are going their own way. But this is very close to the dam, right? And so the dam in this case does matter. And I'm thinking of another way of doing this, but I don't know how much success we're gonna have. So for 2018, you can see the R squared wasn't quite bad. So the phase is kind of good, but the maximum error is we're getting to almost 40 centimeters. And so for 2021, it starts getting really bad. So what are the conclusions from this? One, we've shown by LSTM can capture in the non-stationary tidal characteristics. I would say well, actually, surprisingly well. And the other thing we found, too many neurons don't quite help you. I suppose for people who've been playing with this, say, we knew that, but I didn't know. And also, you don't necessarily need to pump in a lot of hidden layers to get it right. What made me happy is that nobody before this, had ever done any prediction for the non-stationary tides. Zero. So even to go to this little step of 180 hours, I think is really good. And with this kind of operation, if we can reduce the maximum error, we think that could be operational for NOAA. Because that's a week. At least we can give a notice of a week for people to use. And as I said earlier, the success of Vancouver and it depends on what people are doing with the dam. If they decide to open up the dam tomorrow, you're gonna get it wrong anyway. Right? So, yeah. So the next steps here are one, Jim O'Donnell from UConn and his student, she did a good job looking at the tide and some of what we call overtides, the M4 and the M6 tend to be very abnormally large towards the western end. And there is no explanation. And I think with what we found with the LSTM, we can go back now to trying to figure out what are the factors which are driving that. And the other thing is, I still got my homework from Lorraine. So I don't want to disappoint my former students, so I'm gonna go for the currents. I didn't get enough pain, so I'm going to go back and do that. And the other thing is, I'm currently using LSTM. I want to use LSTM and transformers, or Reza will, not me this time, and for predicting hypoxia in Long Island Sound. And So right now, we can't predict hypoxia longer than a week or two. And that is not very helpful for the managers. You want to make it, you want to get a longer prediction horizon. And my goal is to see if we can stretch it to 90 days. And hopefully that will work. And I want to thank some people. I have Michelle. She graduated in December 2023. She was the one working on this, and then all the time she almost like threw it in my face because she was tired. It wasn't working well, and I decided that I should work on it. And we got a lot of help in terms of modeling to figuring out why things were not working from Chin, from a civil engineering. That's Lorraine there. She's the troublemaker. And of course, I blame Christopher for coercing women into learning to do Python is a pain. I keep telling him, and I'd rather do it in my lab. But I learned it too late that all what I did, I could have done it in my lab. Thank you. Yes, yours.
So I can't ask about details, except if you're trying to predict when hypoxia is going to happen, can you also predict how long a hypoxic event is going to last and whether it's going to reoccur?
Yeah, troublemaker. I don't know. I can try, or Reza will try.
Depends a bit, I think, to the time resolution. What is your time resolution? Because for predicting, you should first learn.
Yes.
For learning, you need a very high resolution of data.
And right now we have a monthly data. Any other question? You need to check online if people online. No, there's no question. Christopher.
So just going back to those charts where you're doing the metrics, comparing which factors were important. And all of them at T-tide at the bottom, is it fair to say that for most of them, T-tide actually did better than the LSTM? With the exception of Vancouver.
So, and that's expected. For Bridgeport and Astoria, I would have been shocked if T-tide didn't work, because and NOAA has used the T-tide results forever. The ships would be stuck every day if they were getting it wrong. But if you look at Essex and Vancouver, that's where that's where we want to really apply the model, not where T-tide can. If T-tide can work, why do I need to come up with something else, right? Jack?
So if there were, let's say, coordination between coastal managers who are operating dams and tidal prediction, right? Like, what information could be sort of provided ahead of dam decisions that you could plug into your model to predictions in an operational capacity?
That would make my life very easy, because one, they control the rate, right? So if they say they will keep the discharge at 200 cubic meters per second for the next 2 weeks, I'll be very happy. I'll fix that. I'll just go and plug that in.
But from the modeling perspective, like, how much information do you need and how much time do you need for the model? You know, for the sake of, sort of learning, right? The combination of learning and prediction.
So these were not lagged in any way. So you need it at that particular time, right? Because they are non-lagged. You could do another trick could be, you could say, okay, I'm gonna start doing the lagging and then figure out how much time the lag is important, so the memory is carried over, and then maybe I need a 4 or 5 more days, right?
One imagines that, except for emergencies, they probably know some ways in advance how much water they're gonna let out.
Yes and no. It depends on how much rain.
Yeah, well, for
Well, they have
emergencies,
to
right? Like,
avoid.
if they're like, ooh, there's a
Yeah,
lot of rain,
yeah.
you gotta let more out. But
Once
like,
it starts raining, they want to empty the dam so that it will be able to control the floods.
There's a similar question. If I look at your features, I'm
Right.
surprised. We had the chart. I'm surprised by before that very few features, right?
Yeah,
Driving or modeling.
yeah,
And you would really think, I'm not the expert, but there are all kinds of other features. Yeah, we talked about dam operation might be driven by rain,
right,
fit incorporate.
right,
That should be readily available.
yeah,
And then there must be some, I mean, this interaction when you showed this Bridgeport example, right? Okay. There is you predicted for Bridgeport, and there's a river, Connecticut River, and the other river. I mean, are there other features you can bring in which can help you to model that interaction? Because clearly there's an interaction going on, right? Because what I'm thinking
yeah.
is these 4 features, I'm surprised how good the results look like, but you're certainly not capturing everything which determines it, right? That's about right.
So I try to get all the features that I comb the literature for people. Most of the work has come from Columbia in terms of the US, and if you take the Columbia out, then it's China. It's either the Pearl River or Yangtze River. That's where most of the papers are. And the factors people list, I kind of went through and started picking them. You find that they are not doing anything. And I also try to look at the interaction, not in a I did that in a statistical sense, not in the machine learning way, right? So maybe what I could do is go back and just hire even the ones I think are not that important, hire them there. Because the beauty about the tidal data, I have 20 years of tidal data for all the stations which I use, which means that's about 300 and almost 30,000 data points. They are not independent, but yes.
And then the other question is, have you tried to apply some physics losses instead of MBE or MSE?
Henry, that's why you're here for.
Okay.
Because before you came, I didn't even know what pins meant. Now I know. Yes.
So what if you have a river that's not gauged, but there's a dam? And and you have the records of discharge from the dam. I mean, release of water from the dam. Can you use any of this for predicting what the discharge of the river is going to be into a lake or into a coastal area?
No, because as long as you have a dam, it's there to control flood downstream or produce electricity, right? Or both. And you not know because you are under the mercy of the weather system. And so it won't work. Okay. Seems I've exhausted all the questions. It's time to go for lunch. Thank you very much.